So I have a rotating bar of mass M. A bar of mass M and length L. Rotates with frequency F. Pivoted at one end. What is the kinetic energy of the bar? Okay. So it basically is a situation like this. You know, like I have a little ruler here, right? I place the ruler on the bar, and I just spin it around. So you might ask, what is the kinetic energy of the bar? Okay. For the thing. Well, you know, the formula for kinetic energy is always 1/2 mv squared. But what if I had like a string and I had a mass at the end of the string? Let's assume the string is massless, and I spin it around like that. Well, in that case, if I knew the speed, assuming that the mass is a point particle, if I knew the speed and it's a distance, you know, r away, well, whatever. If I knew the speed, I could just figure out, you know, what the kinetic energy is, 1/2 mv squared. If I want to know the rotational kinetic energy, I could, and we haven't talked about that, but I could, if I know the radius and there's a relationship between the speed and the angular speed. So again, I could figure out the rotational kinetic energy as well, or the V in terms of rotational kinetic energy. So, but the problem with this guy is that it's a continuous mass distribution. So you can kind of think of that if I broke up the mass into differential mass elements, each of those objects would have a different speed. Because even if it's moving around at a constant speed, the overall object, the farther you are away from the center of rotation, the faster you're moving. Now, you know that from like when you were a kid and you would play Ring Around the Rosie or whatever that was. Like, you know, you or whip the snake, right? You grab hands and someone turns, and then, but that person is not, his velocity is, his translational velocity is 0. And then the person around you, they have to go around the circle. So they're going, you know, a certain speed based on the frequency. So this is the center, right? And then this is the next link in the chain. So this person, V is 0. But for this person, they're going around like that. So they have a tangential speed. But if every person has the same frequency, the farther you go out, the faster the people have to move in order to maintain that frequency. Otherwise, there starts to be a bend in the line, and at some point, someone gets whipped off. Right? It's with the snake. You're going, so this person out here is flying around, right? So I'm explaining this because we haven't talked about, there's other ways to explain this from the point of view of rotational kinematics. We haven't gotten there yet, but we don't need that to understand this problem. And I'm giving this problem because it's more like a mathematical problem to kind of iron home some of the topics we discussed in terms of reviewing integration and mathematical methods. So yeah, so that's the problem. We want to, so basically the kinetic energy, if I'm thinking of it as a solid mass, the kinetic energy of each one of those individual parts, differential masses, is not the same because the speed is not the same, right? Like if this is a bar and the bar is pivoted, right? Pivoted and spinning around with some, you know, some rotational speed. And I break up the bar into differential elements, differential masses. those DMs, they don't have the same speed as they move around. So in order to figure out the kinetic energy of the entire thing, I could find the speed and therefore the kinetic energy of each individual differential mass, and then add all those up. And that would give me the kinetic energy of the entire thing, assuming that the differential mass is infinitesimally thin. So that becomes an integral problem for a continuous mass distribution finding. You can't just take the whole mass of the thing and multiply that by, what speed would you use? The speed on the end? Well, okay, fine. But that speed is different from the differential mass in the middle. So it becomes an integral problem. So I'm going to do that for you just to illustrate. This is more like in terms of like mathematical methods. Is kind of mathematical methods. I would say integration. We did mathematical methods earlier where I did a separation of variables for, although I didn't call it mathematical methods, but I like to kind of distinguish between the purpose of doing problems presenting things. And I'm going to do this two ways because I talked about it. I talked about in physics, we like to use mass density where we either have a choice of integrating over coordinates, the coordinate space within which a object exists, like so a mass is going to exist in a volume, and charge will exist in a volume. So we could integrate with respect to the mass, or we could integrate with respect to the volume, or it depends on the geometry. Like in this case, I can assume that it's infinitely thin, so it would be length. So like, as opposed to, if I say it's a bar, basically I could give it 0 width, and I break the bar up into differential mass elements that only have dimensions of a line. So the mass density would be linear mass density, as opposed to volume or area. What I'm saying is, I can think of this as, a bar that just has dimensions of length. I think that's the route to go with this guy, because they don't give any dimensions there, so that's the assumption. You have to kind of make these assumptions based on the way things are asked. So it's really a bar that's rotating, right? I can make it a little bit thicker, but technically it has no thickness. Again, an ideal type scenario, but because if it has a thickness, then it's going to have an area, and it's not a one-dimensional object. Say that it's, so you can see it, something that looks like that. Oh, well, in that case, I could break up this bar into, it would look something like that. So the differential mass would be just that little part, maybe in there, the dm. So in terms of one-dimensional geometry, I would define it's not volume I'm using, it's linear mass density. In other words, I guess I haven't told you this. I should probably tell you this right now. I don't remember saying that in this class, or not at least comprehensively. So yeah, we can, maybe I did, I don't remember. Where is the thing? Oops. Here. Sure. It's a bit much. I just do it here. Oh, wow. So here we'll put like dimension, and the first one-dimensional, two-dimensional, three-dimensional. For one-dimensional objects, we use a linear mass, like a linear mass or linear charge density. Mass is distributed over a line. And the symbol that we use for the mass density is lambda. So name, use the correct lambda, the symbol. And the definition is that it's mass per unit length. So mass per unit length. For two-dimensional distribution of a charge or mass, it will be distributed over a cross-sectional area. And the symbol there is sigma. Sometimes the little thing means M, just to distinguish between mass density and like charge density or number density, something else, because we use the same symbols for all of them. So sigma M. When you don't have a symbol, I think you normally assume that it's mass density, like with rho. So, and this is mass per unit area. And of course, three-dimensional is the mass would be in a volume, and there we use the symbol rho, RHO, and that's this thing that we've been doing, rho, and that's mass per unit volume, which you have already been introduced to in high school. So this differential mass here, we could then use this equation, this relationship, to define the differential mass element. And it's interesting. So I don't give a differential mass here. So in the end, I am assuming that we want the answer in terms of mass, but we can use, just like I did before, we can use, these are given quantities. We can use the concept of mass density just as a tool to do the problem, and then convert back to getting the answer in terms of mass, kinetic energy. So the differential mass element dm, so yeah, let's do here. So if m is equal to well, if lambda is equal to mass per unit length, then the mass is equal to lambda times L. Now in coordinates, maybe that's the length can be measured in like X or something. Maybe I should put that. M or X length. So then a differential mass element dm, assuming a constant mass density, is going to be equal to lambda dx, where x is the length along which the mass is distributed. So here, this dm is going to be equal to, lambda dx. And another thing to note is the differential element is dx, that's the differential length. But it also resides, if I place my origin here, then it also has a position x away from the origin. So the dx and the x are not necessarily the same thing. They're two different things, as you know from integration. So like if I superimpose a coordinate system like here, the thing is rotating about some coordinate system, right? Now I say x, I guess I'd have to use r, but like the position vector that element is a distance away from the in fact, in this case, maybe the best thing, the appropriate variable to use would be r, probably, because I'm a position. I'll just draw it right on top of that. that differential element is a position r away from the origin. That's, you know, r. So yeah, maybe that would be the best thing to use. So the position is r, and the differential space, it was just be have the same symbols, would be dr. So let's just write that like this. Like this. So the mass dm is equal to lambda, what I use in my notes. Yeah, I set it up so that was on the x-axis, but it doesn't matter. It's just, so let's say lambda dr, where r is a difference. So let's put it like this. So length is r, and then lambda r, and then lambda dr. Use whatever symbol you want. I think you get it. Hope you do. Hopefully you do. So because I have two variables, I have options. When I say integrate over coordinates, what I mean is in this case, one coordinate is along the x-axis. So I could do the integral in terms of dr, or I could do it in terms of dm. I have to make a choice. And in this case, just an illustration, I'm going to do both of them for you to show you what I mean. Okay. So I'm trying to find kinetic energy again, like you always just go for the juggler, right? Like, so again, I'll bring out this problem solving template. I kind of changed it up a little bit for integration that you can't really see it well. But we had 5 sections, right? We had, define the problem or demonstrate the problem, which I just did. Then explicit, implicit information, steps 2 and 3. Sketch and diagram, step 4. 5, name the concepts that apply. And the general equations. Step 6, make those equations specific to your problem, and evaluate the zeros, find the unknowns, become aware of the knowns and unknowns, underline them, that kind of thing, and then choose your mathematical path. And then step 7 is work out the problem. Right, so that's 7-step problem solving technique. Basically, can apply to integration as well. So where are we? I go to my notes here. So again, the explicit and implicit information, I basically just know 3 quantities, these 3 quantities here. So what's given is M, L, and F. I guess implicit information, I can assume that the velocity is constant, so it's uniform circular motion. So I guess I would assume that. Assuming uniform circular motion. Also, I'm assuming that the mass density is constant, so I could use this relationship, assuming that the mass density is lambda. All right, lambda and constant v. Now, because I didn't give those values, I don't really know what I can't really give the, I mean, lambda is equal to, I guess I know what lambda is. I guess I could figure it out, right? Lambda for this case, if the length is L and the total mass is M, then lambda equals the total mass over L. So technically, I guess I do know it, but whatever, it's implied because I know it implicitly. So it's part of the implicit information. Okay, so I want to know the kinetic energy of this thing rotating around. So the concepts that apply, of course, are the definition of kinetic energy. Just, I mean, things that I've mentioned. So let's just write it down to be more self-aware. First, the primary concept then would be the definition of KE. The mass density. The definition of mass density. So definition of lambda, just do shorthand notation, which I have there. What else we have? You know, I give a frequency, so we know we have period frequency relationship, period frequency. So I just write that as period is equal to inverse of frequency. And what else? Well, it's velocity. I don't know yet. You know, it's just trying to make up that, you know, we have velocity. We know velocity is change in distance with respect to time. It's going around in the circle. That each element moves around a circumference, which is equal to 2 pi times the position it is at a certain point. I know you might need that. Just, um, I don't know. Yes, so definition of speed or definition of velocity. So definition of velocity. Again, I'm trying to build your problem solving. That's very important here. The idea is I had a whole conversation this morning with my class. Take a little break here and give you a little bit of a lecture. The idea is not rote memorization. And with a problem like this, you might think that you don't have the skills to do it because it's not kind of following some pattern of problems that was worked out. Those are the harder kind of problems to do, like with the, you know, you might remember from your word problems. And that's where you have to build your technique. My technique, as I said, is a 7-step process. And in this case, once you have gone through steps 1 through 4, which I have, you know, then you once you have the concepts of step 5, my general rule of thumb is I go directly for the jugular, as I say, jugular vein as it is, so that you, whatever concept is going to give you the thing you're specifically asking for, you start with that, and you let that lead you through the problem. So I want to know the kinetic energy of this thing, realizing that it's not just one thing, it's an infinite number of things. What things? An infinite number of differential elements. And so if I find the individual, you know, 1/2 mv squared or 1/2 dmv squared, in fact, yeah, I kind of showed you here, but we can do it in terms of kinetic energy. We can do a same kind of process. If the kinetic energy of one of the particles is 1/2 mv squared, sorry, of a singular particle is that 1/2 mv squared, and that's equal to the kinetic energy of, you know, I'm just going to go back, use a simple, well, I've been using KE physics of KE. If I have a differential element that has a certain speed, well, its mass is going to be a differential, a dV, and, or sorry, dm. So I would have 1/2 dm times v squared equals kind of like a dk, I guess you would say, dke. And in that case, this velocity here becomes a variable in this case, because as I said, as you move out, you would have to have different speeds in order to have the same frequency. So the frequency is constant, and the period is constant, but the velocity changes because they have a larger circumference to go around. So if they're going around that larger circumference in the same amount of time, or within the same time, same number of rotations per unit time, then that must mean that the velocity has to be changing, as increasing as you move farther away. So this now becomes a variable. And so to find the total kinetic energy, I add up all the differential elements, not just one, but all of them, which gives rise to, you know, so it's integration. So ultimately, then I can write this as an integral problem where you integrate both sides, right? So the total, this just becomes kinetic energy. So the total kinetic energy, the net kinetic energy, becomes the integral of 1/2 v squared dn. I'll take the 1/2 out, so 1/2 integral of v squared dn. So that's how you would set it up. Now I have 2 options for the integral. I could either do it in terms of differential element dm, or I could use this and substitute and do it in terms of a linear problem where I do it in terms of r, the integration in terms of r. Either one is viable. Um, why don't I do both for you? Sure, you get the same answer. Since I'm on the DM trip right now, let's just do that. Well, to do that, you have to get um, you have to get your so the element is dm. I mean the variable is dm. I mean the differential element is dm. So mathematically, the differential quantity is dm, and v right now v is the variable. So in order to integrate this properly, I mean v is as the dm changes, as I said, the velocity changes. So in order to integrate, I need to get the velocity somehow in terms of the mass. So I have to find a relationship between velocity and mass so that I can write it in such a way that I can put that in and then integrate in terms of mass. Yeah. So does anyone know how to, well, I've written it on the board for you, but I haven't, I think. Have I? Well, I guess I haven't, but you could. Um, yeah, of course I have. Well, you haven't, but there's a way you can do it. So that's the trick. So someone tell me, what is the relationship between, uh, is it between him and, what's happening? Yeah, right. So there's a little bit of work there to kind of think about. There's something that's missing. So I have a relationship between mass and position, the position that the object is away. But if I want to, so I need to figure out, yeah, so I need to figure out a relationship between essentially the distance that's being covered and that position R. So let's take the farthest one out here, the differential element here, because it's just the farthest away, I guess. Well, no, we're dealing with this. So that thing right there is a distance R away from the uh, the center. But as it goes around, it travels around us, what we would think of as the circumference. So I have a, and that we could call, I mean, I guess call that C. If you're thinking about one revolution or just even an arc length distance. In fact, we didn't have to take a whole circumference. We could take an arc length, but I think I did one revolution because we're dealing with frequency and periods. So let's do one revolution. So if it's one revolution, the actual distance that goes around is the circumference. The whole difference is the circumference, C. So if my mass density relationship gives me a relationship between mass and the distance away from the origin, the distance, I need to get a relationship between that distance and the velocity, given that the velocity is basically the time that the object goes around one revolution in one period. Because if I know the frequency, I know the period, so I know that time. So does anyone know what that relationship is? I talked about it when we did uniform circular motion. I wrote down that relationship. What relationship would I need in order to be able to write v, the velocity, in terms of the differential mass? Let me get my t while you're thinking about that. It's a geometric equation, by the way. Anybody? Is anyone there?
Yes.
Well, yeah. Is that you, Didier?
Yes.
Okay. So what relationship would define what could I use for this? I want to get a relationship between R and V. Between R and V. Got it. Yeah. Dami? Yeah, the circumference. Good job, Dami. So that's right. I should probably start numbering these equations. See, 1, 2, 3, 4, 5, 6, 7. So yes, the speed, I wrote this down a while back, is equal to the circumference 2 pi r divided by the time for one revolution, but that's the period, which is 1 over the frequency. So that's a given quantity. So the speed v is equal to 2 pi r times f. That's right. And if dm is equal to lambda dr, then I could substitute. So then so it becomes a variable, I guess. I guess what I have to say is, I'm drawing a blank. Well, I guess I'm doing it in terms of dm, aren't I? So I would have to say that, yeah. So I would use equation 2, right? Because again, I'm going to do it in terms of coordinates. And if I did it in terms of coordinates, I could just plug that in if I was doing it in terms of dr. But I'm doing it in terms of dm. So I have to plug this. Yeah, in fact, let me do it in steps so it becomes obvious. So I know that so this relates v to r, but I have a relationship of r to m. So, well, I guess I could just do it straight out because that's what I started saying. So I need to relate v to m so that I can differentiate. So I would then now substitute equation 2 into 8 so that I could get the r in terms of m. And that's the equation I would plug into that guy to integrate. So let me do that. So now equation 2 into 8. And so now, well, I have to solve it for r. So from equation 2, I would say that r is equal to m divided by lambda. Now, so I guess really it's equation 9. So equation 9 into 8. So then v becomes 2 pi m f over lambda. And everything now, so now, everything in that equation is a constant except for m. M is the variable. So if I square it, because I gotta have the v squared, I just do it up there. Go now. Because I can erase this stuff here.
Professor,
Yes.
I have a question.
Yes.
Can you explain how you like can you explain step number 10 and 9? Like
Yeah.
when you put an equation 9 into 8.
Yes. Yes. Do you understand? So the definition of mass density comes as equation 2. Yes.
Okay.
Yes.
Yeah.
Mass density is mass over, length, and so mass is equal mass density times length.
Okay.
So equation 9. So 8. So equation 9 is just this: solve for mass, solve for length. I take equation 2 and solve it for r. So you divide through by lambda. That's this. Jesus?
Yeah, but I don't see the. Oh, so the r in equation 8 is the length, correct?
Yeah, it's here. R is the distance that differential mass is away from the origin. So the R is
Okay.
this. I had the same color, so maybe it wasn't obvious. I'm running out of colors. Yeah, so this is my R vector right here. It points to the particular differential mass element that I'm using. So yes, that's R. It's the radius of the radius of the circumference that the individual differential mass element is mapping out as the bar rotates. So each mass element has its own R. So that's why it's a variable. So this differential mass element, farther out has a different R. So M is and it also has a different speed. So M is a variable,
Okay.
R is a variable, V is a variable. Got it?
Okay, I see. Yeah. Okay, makes sense now.
Okay.
I was just confused because I thought the L and the R were different.
No. Well, they kind of are. The L is the total length, because when I integrate, that's going to be the limit of R. So good point.
Okay.
The R is the actual length of the individual differential element. But when I integrate, I have to take all the elements, the differential mass elements that go from R equals 0 to R equals L.
Okay, I get it now.
Okay?
Yeah.
Good point. Maybe I should put that in there. So this whole distance here is the distance L. Okay, any other questions? That's a good question. Nobody else?
Thank you, Professor.
Yes. Okay. So now we do, what do we do? Never mind. Equation 10. I have the velocity in terms of the mass. That's what I told you I needed to have in the first place. Because when I was here, I saw I needed to do that. If I'm going to integrate in terms of differential mass, all the variables in the formula that in the quote, the argument that I'm integrating in the integrand have to be in terms of my differential element. So I had to figure out how to get V in terms of M. Now, when I first asked you all that, it might not have seemed obvious because we're not used to doing that. We're not used to differentiating in terms of a mass. We usually do coordinates. I'm doing it here, as I said, for the third time for the purpose of illustration. And then I'll go back and do coordinates. Yeah. And so, but the thing is, and here's the kind of tricky thing is, while the word problems were difficult and kind of making the leap from 5th and 6th grade up till these word problems, is that the relationships that we use to make the connections between variables and differential elements, it can be anything you can think of. It's like it's any relationship you can come up with. Now in physics, we generally try to go for geometric relationships, but it doesn't have to be. It can be logic, it can be anything you can use as a win. And that's the thing that for me was so shaky in math, is because with physics, I'm pretty much I'm a stickler about like protocol and naming the concepts that you use, because it gives me a kind of security that if I have a certain way, I mean, it's kind of like the reason that you like to learn by rote memorization, like when you're doing all the problems or those word problems. There's a pattern that the quadratic equation, for example, has. So if you figure out the pattern, you're not really thinking, there's no higher order thinking going even if you have to do 50 problems in the section, right? You're just following the same pattern over and over again. You might have to think about the arithmetic, or, like if you end up having imaginary numbers or something, like, I don't know. But, like the actual solving of the quadratic equation, that concept, once you understand it, you're just looking for the patterns. So, and we kind of rely on that, right? Now, it's nothing, yeah. So the problem with integration is that there is an underlying pattern. The underlying pattern is that we have to add up stuff, and if you have a formula, like, for example, when we did center of mass, I tried to make that pretty basic, like for you, that, it's a formula that we're using. We're going to kind of apply it the same way every time. But no matter how secure you can be in terms of the concept that involves integration, at some point there's kind of a right-brained element to making the thing work out. I don't know any other way to explain it. In this case, the relationship that I used to make the connection between the variable and the differential element was essentially, I think Dami pointed out, is the circumference. And the definition, two things: the definition of velocity and the fact that for one revolution, the change in distance was a circumference. But for some other problem, maybe it's something else I'm using. There's no kind of rule for that. Like when you do integration problems, you're not going to always at that point, to make the connection between a particular variable and a differential element, use definition of velocity and circumference. You might have to use something else. Like in some of the problems we will be doing next semester, we'll be doing trigonometry, geometry. The other day, I think we used a sine. So it's like, that's the thing that's a little bit shaky in that it's not necessarily the same. And you have to kind of see those relationships. And those relationships don't necessarily have anything to do with the concept you're trying to figure out in the first place. Kinetic energy is not, inherently associated with the circumference when the thing is not moving in a circle. So the best thing that I can tell you is that, and also the other thing is that you're not normally accustomed to having to differentiate for kinetic energy, right? Usually you're dealing with a point particle, and so it's just 1/2 mv squared, right? Here, it's not, because of what we've discussed previously, in terms of you have to look at the different kinetic energy, essentially, of each differential element. So that's even a little bit different. So you're at a point where we're starting to kind of expand beyond just point particles, right? System of particles abides by the same physics, but you have to maybe handle it a little differently, just because you're not dealing with a point particle, right? So this is a time to begin to do that, and to begin to take your calculus and being able to come up with something, applied to a problem like this, where it's not something that you necessarily always have to do. You don't always have to integrate to figure out kinetic energy of a system, but for this problem, you do. So I guess that's what I'm trying to say. You just have to practice and kind of get accustomed to and become aware and maybe comfortable with the element of creative element that's necessary in order to massage a problem mathematically to get the solution that you need. That's a talent to be able to do that. And so you need to be aware that that is a thing, separate from the concept itself, separate from the mathematics. It's being able to kind of, you know, manipulate these equations to get what you need. That's the point I'm trying to make. And you can't get away from it. A lot of people don't like that. They're uncomfortable with integration because of that. But I think I think you just have to kind of embrace it, because it's part of the nature of integration when you start to take integration out of a math class and apply it to the physical world. Right? It's not going to just be some plug and chug thing. You got to kind of figure out, you know, I say manipulation or artistic creative intelligence you have to apply to it, which doesn't means that it's not necessarily going to be the same every time. Anyway, that's it. Let's finish the problem.
I have another quick question.
Yeah.
Why is your v equal to 2 pi r over t?
What number?
Number 8.
This is the definition of velocity. Velocity or speed definitely is delta x over delta t, right? But for one revolution, the delta x is the circumference, c, and the time is the period, t. Circumference is 2 pi r, and the period is 1 over the frequency. So this is one way to write the velocity for one revolution. Actually, if you write in terms of frequency, you're writing it per revolution.
Okay, got it.
Okay. Anything else? So again, illustrating why I like to line this up, right? You're thinking about the actual concepts. It's not about equations. Equations are just a mathematical language that describes the concepts. So, yeah, you know, it's not some arbitrary formula. That formula happened to be the nature of the definition of velocity applied to this specific problem. But I started from my base principle, definition of velocity. Anything else? All right. Well, I was at a place where I needed to plug equation 10 into equation 7 to convert this from this variable to you know, to get it in terms of mass. So we ready to do that? Okay. So equation 10 into equation 7, you have to square it. So the kinetic energy is going to be equal to 1/2 integral. So when I square it, I'm going to get 4 pi squared m squared f squared over lambda squared. And I still have my differential mass of that dm. The constants come out of the integration. So the kinetic energy is equal to 1/2. All the constants are going to be 4 pi squared f squared over lambda squared. In the integral, the integral is just going to be m squared dm. And of course, that goes, this m is small m, it's a variable. So that goes from 0 to capital M, the mass. Capital M is the given quantity. As I add all these on, I'm going to get the total mass of the thing. Uh, 11, 12, 13. So the total kinetic energy then is going to be equal to 1/2 I guess I can go ahead and divide out. So 2 goes into once and twice. So 2 pi squared, frequency squared, divided by lambda squared. And of course, the mass integrates to m3 over 3 from 0, excuse me, for the hiccups, 0 to m. Oh. I want to keep that picture up for now. Of course, that just becomes m, right? Let's substitute in. And what happened here? Oh, I have the 1/2 times the 2. The 1/2 was the thing that was out there. And that effect, no, what? No. How did I do that? That's not right. That's just 2. There's no 1/2 there. That was the 1/2. 2 goes before, so that's the 2. Okay. So that's going to be 2/3 pi squared f squared over lambda squared times m times m, or m cubed. M cubed. But that's a little bit messy, and I don't actually know what lambda is, so I have to put that back in. So I can use the definition that lambda is equal to m over L. So lambda squared is equal to m squared over L squared. So when I substitute that in, I get that the kinetic energy, Ke, is equal to 2/3 pi squared f squared. Now 1 over lambda squared, if lambda is equal to m squared over L squared, it's going to be the same as L squared times m squared. And I still have this m cubed out here. So m goes into m squared, that goes in m squared once, and into m cubed. I don't know, you know what I'm trying to say. And that's the final, and that's it. That's what I need. That's going to give me the answer in terms of given quantity. So 17. So kinetic energy equals 2/3 pi squared f squared. I'm gonna put all that stuff in the parentheses times. Oh, actually, no. Let me do it this way. Let's do it like this. Parentheses. Then I'm going to do f squared L squared. Actually, let's do it like this. I'm going to take the m and place the m next. So m. And then I'm going to do f squared L squared. Now, I'm going to show you a symmetry here. Put that in parentheses too. That's showing you that you definitely have kinetic energy. Remember, kinetic energy is 1/2 mv squared. Well, the 1/2 part, this is just a number. So this is just a constant number, right? The 1/2 is like the 2/3 pi squared is analogous to the 1/2 in the basic equation. M is m, but this term right here, that has terms of, that's velocity, right? Velocity squared. because it has units of meter squared over times hertz squared, but hertz is 1/2. So that's meter squared over second squared. So that's a velocity term. So in fact, I could write it in terms of period, right? It's the same answer would be L squared over period squared, which would be obviously velocity in that case. So that definitely has the right units for kinetic energy, joules. So that would be my final answer. I would do it like that. As a, yeah, interesting. Now I'm gonna let you. Oh, only got, wow, that took a lot. It took 45 minutes. Probably worth doing it though, I think, because I wanted to kind of, this will put a cap on the integration, stuff that we did with the kind of mathematical technique and give you stuff to think about and work on. But why don't you go back and do this problem again? So here I went out of my way to do it in terms of mass, because I know you're not accustomed to seeing integration in terms of mass. But you are accustomed to seeing integration in terms of coordinates, dx, dy, dz, dA, dv, for differential area or differential volume. But again, in physics, we like to do that so that we try to convert those things to single integrals of single variables. In this case, I have assumed that the mass is a one-dimensional rod. But even if it weren't, I would still use the technique that I did the other day. Like if I gave this some sort of volume, well, the volume is going to be area times length, where the area is constant and the length changes. So either way, it still goes back to an integral over a single variable, right? In other words, if I'm saying this were actually a rod that had cross-sectional area A, then the volume would be that area A times the length. But when I break it up into differential elements, the area is still pi r squared. So it comes out. So it would be over here with the constants, and I'm still integrating in terms of length. So whereas I didn't have to do the triple integral because the area is constant and I know what it is for a bar or for a rod or whatever. So I don't really have to make it a triple integral. I can just choose my differential element where the area of which each of those differential elements I know, which is a constant, which comes out of the integral. But that said, I want you to go back and do this problem again. Take a few minutes to do it. Go back to step 7. In step 7, I purposely chose to integrate with regard to differential mass, which meant I had to convert my variable to something in terms of m. Here, I want to do the integral in terms of coordinate. So that means that I have to figure out how dm relates to the coordinate, in this case length, and I have to figure out how the velocity relates to the coordinate length that I'm going to be integrating over, which is r. And everything is here for you to do that. So it's just a matter of going back and doing it, and then going through the integration. And in the end, you're going to get the same answer. So does everyone understand what I'm asking you to do? Okay. The difference between the small mass and the cap. It's the same question. Who's asking the question? Didier. Oh no, Dami. It's the same question that, basically the same question that Jesus asked me about R and L. R was the variable, L was the maximum length. In this case, dm is the variable. So m is the actual mass of the differential element. It's how much mass is. I mean, we're saying it's a differential, so we're saying it's infinitely small, but we still have to have a variable that represents that because it's in the equation. So to answer your question succinctly, m is the mass of the differential element, and small m, and capital M is the total mass of the rod. So small m is a variable, large M is a constant. Small r is a variable, large L is a constant, the total length. Okay. So does everyone understand what I'm asking you to do? I want you to go back here and do the problem again, but convert dm to what it would represent in terms of coordinates, dr, and then figure out what v would have to be in terms of r so that you could have both your variable and your differential in the same units or the same quantity representing, namely r dr, and then integrate to figure out what, and then get the answer. Take a few minutes to do that as we go. So I know these problems, I do the more intermediate to difficult problems in class because I think the other ones are kind of a waste of time. It's not a waste of time. It's just that we have to be efficient, right? So I want, I would encourage you, all this classwork stuff, when I tell you to do something like this, put effort into it. When you go home, like we don't do it in class, do them, finish those problems, particularly when it has to do with all of it. But definitely these problems, we did the thing with this. It's a little bit extra, actually, a little bit. Working out the details for separation of variables for drag, doing the integration problems here. Over the years, I found that this is a better preparation, even though technically you don't really have to do it or spend quite as much time as I spend. It makes a difference as you move up. When you spend the time to go through, even if you don't get it all perfect, because particularly now, there's probably not going to be any integration problems on your tests. They usually kind of do that. That's why they put so many graphs on those kind of digital tests, because you can kind of get concepts of integration or the similar concepts by illustrating them graphically, which is a nice thing to do. And I just don't have time. I'm still trying to build these classes so I could actually go in and put the problems in and figure out a way to ask you how to do the problems in. But I'm not going to, I just tell you straight up, I'm not having time to do that just yet. But still, this is part of my lecture. So even though you're probably not going to test you rigorously on this particular thing, it's worthwhile for you to go and do them when I ask you to do them, because there's value in it, and it's very helpful for next semester, because you hit the ground running in electricity and magnetism, having to integrate, Coulomb's law and electric field and force and magnetism. Is integration all over that place in that class. And because I don't lean on the calculus at the beginning of the course, which I told you I didn't, I derive all this stuff with algebra. This is the place where, now that we've warmed up and what my kind of lecture style, and these are good problems to do. All of these kind of problems I do in class. So I would try to do them and do them, have them nice in your notes so you can refer back to them and you remember what you did. So take your time and write them out well, so that 3 weeks from now or next semester, you might be able to look back and even make more sense of it now. And it'll be helpful for the things that you're doing then. Whether you have me or someone else. So work on it a little bit more. Any questions? We should try to see if you can get through it.
Professor.
In fact, yeah, go ahead, Dami.
So what you want us to do basically is we replace the M with what you defined early on instead of integrating DM. Then what that will be to include DR. Then we'll be integrating DR. Then L will be put into the equation.
Not L. L is going to be the limit of that length. If what you mean is R, then that would be correct. R would be in the equation. L is the maximum limit of R. R goes from 0 to L. So I wouldn't use L because
no, I mean after you integrate DR.
Yeah, then the limit of R goes from 0 to L. That's right.
Okay.
Now, again, it's not just a matter of substitution. Like that would be easy. Like DM is equal to DR. There's a relationship that you have to figure out. What is the relationship between DM and R? Because it could be straight, but it won't be obviously because that would be that saying that length equals mass. It doesn't. So that's what that whole soapbox I was selling a few minutes ago. It's kind of the concept that relates them won't necessarily be a physics concept. It can be any concept you want as long as it's right. That's the thing I'm trying to say with integration, that it can be anything, any concept, that you could possibly think of, whether it's geometric, mathematical, logical, whatever, that relates M and R. If you could find it might even be some other discipline like chemical or something. I don't know. Like I'm just not likely, but like whatever. Anything that works. It's true. And then once you do that, the same thing with V. What is the relationship between V and the integration variable that you're using? Any concept and equation that relates them from any discipline that you could possibly think of will work. So it becomes kind of an art form to think about like how you could find clever ways of transformation is what it is. It's transforming that integral to the other space in which that integral variable represents. I use the term space in general, because we usually integrate over coordinates and coordinates define space. But then I use that terminology like, to represent because I don't know the mathematical terminology. But I think you get what I'm saying. So that answers your question, right?
Yeah. Thank you.
Yeah. I'm going to leave that solution there just so we have something to compare it to. And then go ahead and work through the rest of this. In red, I'll leave that one there. So let me just start right here. I can erase all this too, I guess. Well, the DM, I think I had written that somewhere. I'll just write it again because I've erased it. It's lambda. So lambda is, M is lambda is M over R. And that's also dm over dr. So, yeah. So that means that here. So that means that dm is equal to lambda dr. So, and then for the velocity, I probably had it down there. I should have erased that. So I need to get velocity also in terms of, so speed is going to be 2 pi r over the period, or 2 pi r times the frequency. So yeah, so that's going to do it. It's just equation 8 and 9 that I substitute in. And so I'll get, how is this happening? This is black. How is this? Oh, I think I had it wrong. Okay, whatever. Yeah. So what am I doing? I am, yeah, so substitute 8 and 9 into 7, you're going to get the kinetic energy is equal to 1/2, and that quantity squared is going to be 4, so the integral of 4 pi squared r squared f, and then the lambda is, the dm is lambda dr, right? So then integrating, that the 1/2 and the 4 will cancel, give me 2, so 11. So kinetic energy will be equal to 2 pi squared. I get it. Oh, that's f squared. And it's also, yeah, so the lambda is not squared, is it? No. So then f squared is outside, lambda is outside. On the inside, I have r squared dr. Right. So of course that integrates to r third over 3, and the limits are 0 to L. So the one version of the answer is 2 pi squared f squared lambda and L cubed. But yeah, this is it. So we want to match up the answers. And I left out the third. The third comes over, the 1/3 comes over here. So the third is there. The answers have to be the same. So here I take the lambda out. So 12, 13, 14. Remember, lambda is equal to m over L. It's here. Well, you know, that in terms of total mass, these are variables and differential, but in terms of total mass is also total mass over total length. So 3 or 4 different equations involved in that definition of lambda. And once I put that in, then I will have KE is 2/3 pi squared f squared m over L cubed. Of course, one of the L's cancels, get the square term out, and then I can write it in the form that I have over there. That total kinetic energy is equal to 2/3 pi squared quantity, and then I have the mass, and then I have f squared times L squared, which is speed in terms of frequency and total length. So a bit of mathematical methods for today. Integration. Questions, problems, troubles, gripes about that? Give me some feedback, response. What do you think about that? Anybody? Muhammad, what do you think about that? Muhammad, you there? Tommy, did you get the answer?
Yeah, yeah.
Good. Abdul, did you?
Yeah, Dr. Brian.
You say again? Did you get it?
Yes, I'm good. Thank you.
Good. David Edwards. Is this making sense? David, you there? Okay, maybe not. Thank you, David Wapple. And Didier.
Yes, Professor.
Yeah, how were you able to get the second part?
I got up to midway through, and then my son had a little accident, but I understood it.
Okay. Tell Anakin I said hi.
Will do.
Okay, let's skip to momentum. So we had started to discuss, we talked about momentum a little bit already because I gave you the version of Newton's second law, which now will come in handy.
Professor,
But yes.
I had a question. I'm not sure if you've answered this already, but what we just solved right now for kinetic energy, is it the same? Is it something that we'll use, like, when we have the initial and the final? Like, will this come up at some point there too, when we have potential energy and?
Actually, no, this is a different way of figuring out something like that. So that concept is conservation of energy, and it would be predicated upon knowing the energy at two different points. In this case, or two different situations. In this case, the energy is constant, so there's no change in kinetic energy. So it's not, you wouldn't have, applying conservation of energy to this wouldn't give you the amount of energy that it has. You know, conservation of energy says that the change in energy is zero, or mechanical energy is zero, but it implies that the mechanical, so that's the total mechanical energy is not changing, but between two time periods or two positions, say some of the energy kinetic will have to be converted to potential or vice or something like that. In this case, I'm assuming it's just spinning around on a constant surface. So the kinetic energy is constant. It's not changing. There's no external forces doing work on the system. Overall, there's no network done. So I don't think you could apply conservation of energy to this problem given the way that I set it up to solve the answer. One, but two, in general, this is just, it's basically just figuring out the kinetic energy from kinematic principles, from the formula 1/2 mv squared. But you're just not given, so first of all, even if you knew the velocity of the thing, it doesn't, the average velocity of it spinning around, or knew the angular velocity, you have to be careful because each individual part of the object has a different velocity and a different kinetic energy if you break it up. And so you have to figure out a way of adding that up. And so, you have to use calculus otherwise to get an exact value. Otherwise, if you just break it up into delta m's as opposed to differential m's, then you're always just averaging the amount of velocity that it has, that the delta m has. So a differential m is just kind of a strictly it's kind of more of a math problem, that this is the way that you would have to do it if you could only use math to figure out the kinetic energy. If you could only use calculus, let's say, to figure out kinetic energy. I don't know if I answered that well, but yeah.
Thank you. I understood. So what would happen if it wasn't constant? Would we lose a variable? Would we add? Well, I'm assuming we'd be adding something to it, right?
That's a good question. That means that, ooh, how would we do that?
Would it be like fluctuating, or would that just depend on the system?
I mean, it could be fluctuating. It could be fluctuating. In which case, that's a really good question. And this is the answer. In this case, the velocity just depends upon r. So this r here, oh, that's a very good question. This v is just dependent upon r, because it's equal to 2 pi r over a constant t. Yeah. But if the velocity were fluctuating, that means it's fluctuating about the arc length, a particular arc length s, like its speed along that, the tangential speed v is changing. So that would mean that this t is not a constant anymore, it's a variable. So this would change from a speed that's dependent upon one variable to a speed that's dependent upon two variables. It would be a v of r and t is equal to 2 pi r over small t, over small t. So I probably wouldn't, yeah. So therefore you could do it a couple ways. You could either write it like this, or you could write it like, so it would change it to a double integral, basically, and not in space, but in f and t. And you could do it a couple ways. You could do it in terms of dr and t, or you could do it in terms of frequency. You could integrate it probably in terms of frequency. And that's a little bit, where would the variable come from? I guess I would have to figure out, wow, that's a little bit tricky, because it's a little bit easy to figure out how velocity depends upon time, but how would the mass, uh, well, the masses, how would that, how would you, okay, I think you'd have to do some sort of parametric equation type thing. And I'm drawing a blank on how to move forward, but that's how it would change. Like the velocity now would be dependent upon time as well. And so I think I might have to parameterize this to figure out how to get, so this is done, but I need to figure out how the dm depends on time. And remember, the dm is a differential element, but still they would take the same time to go around. Would they have a different frequency? No. I'm not sure how to, what would I do? Or do I have to get time in terms of r, or r in terms of t? How could you do that? The r, yeah. I think that, so this is, I got this far, but then you'd have to figure out some way where you could figure out how T changes relative to R or vice versa. So maybe you wouldn't have to change the DM in terms of time, because it doesn't really seem like that changes in terms of time. But I think you have to do, and I don't know how to do that right off. I have to go and research the calculus book and figure out. It becomes a more complicated problem though. Or maybe, yeah, yeah. You got me thinking. Comes from dx to t. So p is equal to dx, t for the x, p is equal to 2 pi s is equal to r theta t s. Yeah, I do know how to do it. You'd have to go back to this, and you'd end up having two terms. You'd have a radio term for the speed, and you'd have, because of, yeah, you'd have a radio term for the velocity and a centripetal term for the velocity. Both of those would change. The way to do this is maybe we'll revisit this problem when we do rotation, maybe. It still would be, even in that case, it would be an intermediate problem to advanced problem, but it's not, it's a little bit more advanced. There's no t, it's going to be a dx dt, and you get two terms. Then those terms you would put into this equation and would break it up into two integrals, one for the kinetic energy for the radial velocity and one for the kinetic energy for the centripetal velocity. And the total kinetic energy would be the radial kinetic energy plus the centripetal kinetic energy. Associated with the radial and tangential speeds. And I think the problem might fall out like that. It still would be a scalar quantity because speed is scalar and you have the square term in there. But it might, once you do that, it might actually turn out pretty easier. It would turn out like not as difficult as I thought. Yeah. That's how you do it. I know I got off on a tangent, but does that make any sense? You see where I'm going with that?
Oh yeah, definitely. Yeah, sorry I brought that up. I just remember seeing something where there was I don't know if it was like an object in space, and I remember seeing something similar to that.
Oh yeah, yeah. Those probably, yeah, probably orbital motion in because this is definitely a problem associated with it. Yeah, it's orbital motion or But there's other methods there that you can look at that are a little bit easier that we haven't talked about yet. But like conservation of angular momentum is a route to go. But again, that has to do with the change in angular momentum or the change in kinetic energy between two different points, which is not quite, it's a different approach than this. So you don't have to do the integration point. But I think it's, if you can work out the integration without too much difficulty, it's probably worthwhile doing. I always try to do more than one method if I can. But yeah, you would see problems like this in orbital motion. That's right. Yeah, cool. Cool.
Thank you, Professor.
All right. Yeah. Mm-hmm. So let's go ahead. What time we got? So we got an hour, 10 minutes. Okay. Sorry, I got an itchy, scratchy throat. All right, let's try to make some progress on this thing here. Remember Newton's second law. I said that, Newton's second law is equal to mass times acceleration. But acceleration is m dv dt. And if I take the m inside, m doesn't have to be constant. So in general, it's ddt of this quantity m times v. And that is a thing. That's a physical quantity called linear momentum. We use the symbol small p. Is defined as mass times velocity. So if you substitute it in, you can also say that the net force is equal to the time rate of change of the linear momentum of a system. So these two equations are synonymous, physically synonymous to one another. So the second law can be stated as net force is equal to mass times acceleration, or net force is equal to the time rate of change of linear momentum. So it's definition of momentum. It's a vector quantity. So momentum is a vector quantity. Or linear momentum. Definition. Linear momentum is properties. Is that it's a vector quantity. It is it has units of kilograms, meters per second. It doesn't have name. It doesn't have a name. It's not named after anybody or anything. So kilogram, meters per second. Now be careful because that also is the same units as that's units per second squared. So now scratch that. Yeah. Yeah, you can write Newton's second law in terms of that and momentum of system particles. You can have, we talked about systems of particles, and the same thing, superposition applies. So if you have a set number of particles, the total momentum of the system, which is usually denoted by some sort of script capital P, is equal to the net, the summation of all the individual peaceabides of each system. So that's also consistent with any other quantity that we said, like the total velocity of the system is equal to the net of all the individual velocities, the external force, all that stuff, so basically superposition principle. And again, this is the same, this is applied to a system of particles. In the system, we talked about that on Monday, where I drew all the different particles through the axis, we found the center of mass. So that's what we mean, the center of mass of the system of particles. Basically, this is the momentum of the center of mass, essentially. So two basic things we want to discuss in terms of momentum, other than the definition. One is conservation of momentum, and one is the concept of impulse. Why don't I do, in my notes, I have impulse first. Okay, wow, fair enough. Sure. And then we have to launch into collision. We can use both of those to talk about collisions. All right, so impulse. Okay, so impulse, when do we use that term? You use it probably in lay term, when you're not talking about science all the time. Like if you say somebody is impulsive, what does it mean that someone is impulsive? Or a decision was made impulsively. What does that word mean? Anybody? Come on.
Acting like without thinking.
Yeah, or it could be thinking, but thinking, well, yeah, without thinking. Let's go with that.
It's just a random something like erratic decision.
Erratic, I like that word. Erratic implies something about time, or I guess it kind of can. Maybe not directly, but when you make decisions like that, what normally, what type of time period would you associate with an erratic decision or an impulsive decision? Long, short, long or short?
Short term.
Say again?
Short term.
Short time, yeah. So impulse implies that whatever the action that's happening, whether it's a thought process or an action, is happening over a short period of time. So relatively short period of time, small delta t is inherently associated with impulsive decisions, and in physical sense, it's the same thing. That an impulse is something that happens over a short time. And the something that we're talking about is force. So an impulse is related to force. Basically, impulse is a quantity that defines force interacting with the system over a short period of time. So that's how I would qualitatively define impulse. Impulse is a description of a force acting on a system in a short time period. Impulse is also related to momentum, linear momentum. Okay. So let's investigate. The definition of impulse, I'll just start off by saying that. So we apply to things like, I said force over a short amount of time. So something like hitting balls, a ball bouncing. I don't have any balls in here right now. Tennis ball or basketball is flat. I don't have anything. But like if you throw a ball against a wall, the time in which the ball is in contact with the wall, the collision, is a relatively short amount of time. Maybe even less than a second, a couple millisecond or half a second or something like that. Same thing as hitting a baseball. That's an interaction where external force is applied to the ball over a small amount of time. Any kind of ball, basketball bouncing, softball, hitting a softball, hitting a golf ball. All of those problems are impulse problems. Even collisions to some degree, we can talk about bumper cars hitting. There's usually a deformation that occurs in the ball or the bumper or the car if it crashes. And that happens over a relatively short amount of time. So the issue is impulse gives us a way of averaging. The thing is, when you think about a ball hitting a wall, it actually will deform. And so the amount of force that applies to the ball over that time period is generally not a constant force. It's in fact, you might kind of say that it could be approximated as a Hooke's law force, because the more the ball compresses, the larger the force. And if there's no deformation that occurs, the relationship between the force and the deformation or the change in length is usually linear. And that's a Hooke's law, like force is equal to some constant associated with the ball times delta x. We don't really have to get into that because we're not going to look at the function of form. It can be related to other things, because generally, like if it's colder, the ball will surely respond much differently than it's warm for the same ball and the same wall, even atmospheric pressure and things like that. So it could be a really complicated situation. But what we do know is that on the average, if you look at anything, whether it's a ball hitting a wall, basketball bouncing, golf ball, anything, you might, if you thought about how the force relates to time over the total distance of the deformation, it's not linear in general. It's but it looks something like maybe an S curve. So like, certainly, let me just say what I mean. In fact, I said linear. That's not really true. That's our first approximation, but in general, it can be much more complex than that. So let's say we have, looking at, this might be some sort of question I would give you if I were testing you on this. Like if I rolled out a question for a test. So let's say we have a ball. Let's look at 4 different points. Here's a wall. There's 4 snapshots of the ball approaching the wall, making contact with the wall, coming to, rest in the middle of the impact, and then rebounding and going back in the opposite direction. So this is just snapshot, 4 pictures of a wall, snapshot. Now, in this case, let's say the velocity of the ball is going to be going into the wall, hitting it. In this case, the velocity is coming back away from the wall. These guys down here. Okay, so draw a picture of the ball. It's a lot of drawing to get maybe a little bit of work, but this has proven successful illustration in the past. So 4 snapshots. So here's the ball on its way to the wall, and then the ball just makes contact with the ball. So it hasn't deformed yet, but just on the edge of making contact. Then it starts to make contact and starts to deform a little bit. Then it makes maximum contact and deforms so that it's kind of squished. And then it bounces off and comes back in the other direction. Right, so squished and then, right, then kind of coming back, then away from the wall. So here the velocity is still going in. So V equals 0, V equals 0, then bouncing back. Yeah. And if I were to draw a picture of the force on the ball, here there's no external force, assuming no drag. Here, just 0, maybe just as it starts to contact, you start to see a little reaction force there. Then it gets a little bit larger, and here it's a maximum. I probably should draw from the center of mass, but it's like the normal force. It's the normal force, and the normal force is changing, right? And then here you kind of back off. Maybe it's still there, same thing here, and then maybe like that, and then like that, right? And then no external force. Now, if let's say that this distance here is the diameter of the ball. Do I want to say that? Because it doesn't squeeze all the way. I don't know. Let's just say that we start our clock here, or not a clock, but we start measuring basically, yeah, I don't know, is it time or I'll give you some time? Yeah, I would do it. Let's do it in time. So if I wanted to sketch out a curve that represented the force per unit time during the entire time of the collision. So basically T naught is 0, and that starts, well, here. So this is T, and this is F of T. And I wanted to look at the time from, T final represents this time right here. So T initial is when it hasn't made, just when it's about to make contact with the ball, and then comes back, and T final is like right when it leaves the wall. If I sketched out that curve, what do you think the curve would look like? What is the relationship between this normal force changing? How does it change relative to time? Think about that for a few seconds, then I'm going to give you answers so we can move on. But when people ask you that, like the basic curves that are, linear, quadratic, or some sort of power function, doesn't have to be quadratic, exponential, or maybe some combination of all of those. I kind of led you wrong. I think I said something about linear, but that's only not really true. That's probably a very small regime. But overall, actually it is in a particular regime, it could look a little linear, but I'll show you where I want to be. But it's not, in general, it's not linear. I'll give you a hint, actually. Has anyone in here ever done any of that network marketing type of stuff? Like when you're selling stuff, network marketing. Some people call it a pyramid scheme, which it kind of is, but it actually is a legitimate business model. It actually works for people who are into that kind of thing. It's not a pyramid scheme well, I guess it depends on how they set the business up, but it's not it's a legitimate business model. And has anyone ever done anything, or people going to any of those seminars or sat down and have someone try to get you into one of those businesses? And I'm talking about someone who actually knows what they're doing, who does it well, not someone who's just learning and trying to learn how to. Anybody had any experience at all with any of that? Anybody know what I'm talking about? No one knows what network marketing is. Really? No one's ever done any of that. That's hard to believe. This thing is like this. Wow. Yeah, this business model has been around for 100 years, like maybe since the mid 1900s. Well, yeah, okay. Well then that's not a reference. I guess no one has done anything with specific heat or heat capacity or anything like that. Yeah, so I guess I can't draw on that. So that's curious. So no one, Dami, you've never heard of that at all?
I've heard those businesses like the online business and everything. The thing is, I've not joined them physically, but I do watch the seminars sometimes, like how to.
Okay.
Yeah.
Okay, cool. You watch the seminar. That's all I need. Yeah, you have to. Yeah. So if you've watched the seminars, do you ever remember seeing any graphs that they'll show you about?
Yeah, they have graphs.
Yeah. What is the main graph? Like any of the graphs, it's probably gonna what if it's an analog like kind of an analog, what does it look like?
Well, the graph is not like a straight line. It looks like more like a biology graph, like it's jittering. I don't know. They have like all these type of lines showing the markets and everything.
Showing the what?
Showing markets, some show stocks, some show
The markets. Yeah. So they'll show you like they particularly when they start to give the hook, like generally if it's and it's different things. Maybe it's a product or maybe it's selling other people's products. It all follows the same kind of path in terms of they'll talk about saturation of people in the business, and they'll give you a specific curve, whether it's people saturated or whether it's people or items that people are going to use. But there is a specific curve that is a curve that has relevance in physics, ooh, and in any kind of hold on just a second, I gotta take some medication. Any kind of system where what day is it here? This is Wednesday. I did take one. Yeah, I don't enjoy this out. So yeah, I guess what I'm so do you remember any of the shape of any of those curves? And it would have to be a more analog graph, not a graph that is pie graph or something like that. I'm talking about, and it probably would have been associated with saturation of the product or saturation of you know partners in the business, where you would have seen a curve like this, to the one I'm trying to allude to. No, does any remember any? And it actually has a name, which if they were really good, they probably referred to it with the name of the type of curve it is, which is not specific to business, but it's the same type of curve. We call it the same thing in science. Anybody? David? No. You remember any?
Nah, I don't. You can't really. I
Remember?
can't pay attention to what they're saying, but the graphs. Like,
Okay. What I'm referring to is something called an S curve. An S curve. It's a signature curve that defines essentially the saturation of a lot of types of systems in nature. And it looks something like this. And it kind of goes up and it's going to reach a maximum value at some point. With a maximum value in science, well, they might have showed it there too. Might have a dotted line like this, something like that. And this curve basically approaches that line at some time period. And what they say a lot of times is that, oh, well, we just started, we're down here in the business, and at some point, some critical point, like maybe right here, the business is going to take off. It's going to be a lot of people. So you want to get in where that's the pitch that they use. The thing is, though, they're right. This is a standard S curve is a standard curve that that many systems, it's like an average value of the way something would behave in time or whatever the independent variable is. In fact, another thing is this is also that's economics. So yeah, they're talking about business, but even on Wall Street, S curves are hugely popular. They are hugely significant because they kind of give you an average value of how some new capital or new business would infiltrate a system, right? But interestingly enough, it also shows things like heat. Like if you put a donut in the oven, and you wanted to look at how that donut is taking on energy on units over a time period, the curve would look like that. It would be an S curve for the same reason. The heat is interacting with the molecules. First, the molecules on the edge, they take it and they start to vibrate. But then as those molecules heat up, the molecules deeper in the material, they're getting heat from the vibrating molecule, but they might also experience heat from initially they would kind of also be interacting with heat from the outside. But as you get deeper in, and so at that point, maybe that's when some critical thing happens, and the molecules maybe a couple levels in are getting heat from both the outside and from inner molecules around them that are starting to energize. And then there's a critical point where it shoots up. But then as you get farther deeper in the material, the amount of absorption starts to slow down because the outside heat can't penetrate as much. It's only the molecules are only getting heat from the next molecules beside them, but they're deeper in, so it happens less and less. And at some point, maybe all of the molecules will be saturated with the amount of heat that they could take, and beyond that, the thing with the donut is going to burn up, or if it's water, it would evaporate, it would change its state. But the way the heat would it would absorb into the material, it would be something like an S curve. Now, we were talking about the force on this, but think about it. These are atoms in here, and they're being compressed, so they have a resistance. So, the harder that you push something, the harder it is to compress it. But if you actually did it, it wouldn't, if you know what you're feeling, it's not a constant amount of force. Like initially, it's easier to compress it, but the rate at which it gets more difficult is also not constant. It's probably hard to really get a sense of that for a small ball. But if you had like a balloon, yeah, you definitely could see if you knew what the curve looked like, you could feel the compression is different at different places. It's not just a linear kx type of thing. It's changing. The amount of force or resistance is changing even at different points of the compression. Basically, it has to do with the fact that the atoms, kind of a similar thing to what I said about the heat, the response of the atoms is less initially when you start to compress the thing, and it starts to get more resistance as you compress it, but still it doesn't happen in a linear fashion. And so the force over a period of time of the compression, it would look like an S curve. And in an ideal case, when you start to back out, so basically this curve would describe the compression up to a maximum point. And then as the thing backed out, you would have an S curve in reverse, right? Which would look like that, which gives another very famous curve, which you probably didn't realize where it came from, is this curve actually also has a name. What type of curve does this look like? What is this called? Anybody? That's a specific kind of curve as well. What is it? What type of curve is that? No one's heard of that, seen that before. It's the same type of curve that defines grades in the classroom. Like if I average your grades on any test or anything, the grade distribution would distribute associated with a curve like this. I don't know if anybody's had statistics yet, but all this would be like in the statistics class. You probably look at something. So curves might kind of do something like that. But the average value would be the name of this curve. If I tell you, you're going to know what it is. No one knows? No one? Jesus, you never heard of any curve that defines what I'm talking about here? Is anyone there? I know somebody's there. Nope.
They're not hyperbolas or parabolas, right?
No, that's not a hyper. No. What I'm talking about is Gaussian curve. This is a Gaussian, or a bell curve. That's kind of the lay term for it. Gaussian distribution. No one's heard of that?
No, I've never heard of it.
Okay. All right. Well, you still what level of math are you doing right now? Is that Abdul? Who said that?
Kel
Yeah,
2?
Abdul.
Yeah.
Yeah. Okay. Y'all still kind of a little bit young, so that's cool.
Kel 2.
That's cool. You might not have seen it yet, but you will eventually. You'll see it somewhere, and probably even if you don't talk about it, it's usually a statistic thing. If you don't take statistics, you won't deal with it specifically, but you might see little examples or applications in calculus as you start to get to calculus 2, calculus 3, where they mention something about that. But it's interesting that I mentioned the S curve because they won't tell you that the S curve is kind of like the Gaussian S curve and kind of together. But that's how a Gaussian is generally made when you look at a distribution like that. So I mentioned all of that because what we do with impulse is that if you know graphically, they might, you might see a problem like this graphically, where they might not get into the background of a Gaussian and all that, but they'll just get it. But the average value, so this thing is very difficult to get the functional form of a force because it could be dependent upon a lot of things, depending on the material, depending on the temperature of the air, depending on, like the speed that it hits, I don't know, like it's, and you would have to know all of that. We just talked about the dependence of this last problem we did. This force this is a simple Gaussian where it's dependent upon just time. But the Gaussian is, but the actual force distribution might look something similar to this, but to get the specific force, it's going to be dependent upon other things, not just the time. And so it's really difficult to figure out what that dependence is because it can be really complicated. And so what we do is first assume that it's the force changes with a simple distribution like a Gaussian, but even that we still don't get the exact value of the force at any time. What we say is we could approximate the force because the average value of the force over the time of the collision is going to give the same result in terms of acceleration and anything that we wanted to use the force to find as would knowing the exact force at any instant of time would give us. So we basically deal with the average value of the force, which is about half the value of the force over the Gaussian, from the 0 to the maximum. It's not really half, it's actually a specific value that I want to work out right now, but its average value would look something like that. And so we use that to define the impulse essentially for a constant force. We say that the impulse is equal to the average value of the force over a specific time times the time. And we do something like this. We'll say impulse. Yeah, come back over here. We say that impulse is now some people use different symbols for impulse. Some books use capital I, but I kind of get them. I don't like to confuse that with current, so I'm going to use a capital J. Impulse J is, and I know I use that for current density too, I think. Oh no, that's a different class. But is the integral of the average value of the force squared to time times dt. Actually, that's the specific value of the force. But a lot of times, so that if we could substitute the specific value for average value, and so the average value is always going to be a constant. So that's one way to describe impulse, because you might be able to figure out for some ideal problem what the specific force is, the force function. If not, though, or you just might be able to make something up theoretically. But if not, in general, you only know the average value of the force, and that's and so you know that over some small displacement of time. So this is more what you would apply to a baseball or ball being hit, because you're not going to know the actual force. So the average value of the force over a small amount of time. And if you look at this from Newton's, so the relation, so that's kind of the definition of impulse. It's defined that way. But because of Newton's second law, there's a relationship that impulse has to momentum. And so if we start with Newton's second law, that the net force on an object is equal to the time rate of change of momentum, realizing that if the force is an average force, then we can say that an average force is equal to delta P, the change in momentum over a change in time. So then we take it over, average force, delta T equals a change in momentum. So that gives us more of a practical application of, and so this is actually impulse, right? Because F times delta T is defined as impulse. So we can also say that the impulse is equal to a time rate of change in momentum. Momentum final minus momentum initial of the system. So if the momentum is changing, then we can define the impulse by the change in momentum. So like here, you could determine the impulse, J, on the object as it goes from its maximum velocity just before it hits the wall to 0 right at its full impact. Right? And then the velocity would change again as it rebounds out. And be careful, impulse is a vector and change in momentum is a vector. So you might be tempted to say, like if I had an ideal problem where I said, there was no energy losses and it rebounded with the same velocity that it went in. So which means that the magnitude of the impulse would be the same hitting as coming out. You might be tempted to say that the total impulse was 0. But impulse is associated with the force of the ball on the wall. So you know that can't be true. The thing is, remember there's a sign change. Momentum is a vector, so the momentum has a different direction, even though the magnitude could be different going in, or just before it hits the wall as just before it leaves the wall. So you'd have a minus in here if you worked out a problem like that. And so the impulse would be twice in that ideal case, the impulse would be twice the change in momentum, or twice the magnitude of the momentum, twice the magnitude of the maximum momentum in that case. So 2 equations then for impulse. One is the definition of impulse that is equal to the integral of F versus T. And one is the relationship of impulse to momentum. The other thing that's used a great deal with momentum problems that you need to know is that we've looked at the area under the curve twice now. We saw that when we graphed the velocity versus time equation, that gave us one place where the area under the curve was the displacement. All right, so we got something like that. V of t equals V naught plus A times t. All right, when you graph that, T1, T2, V1, V2, what we saw is that this area under here was displacement. So that was one place under the V versus T curve where area under the curve had some physical meaning. The second time was work. Plot F of X versus X. Again, make it linear, make it a spring, FKX, where that's X1, X2, F1, F2, right? The area under that curve was work. Work is equal to F dot, delta X. The third place that we see that is here. And I'll just use this curve over here. This is F of T versus T. Well, look at this equation here. That's F of T times T. Now that's not a linear relationship, so I won't be able to draw a quick line like that, but the units are the same. F times T means that the area under the F versus T curve is impulse. So you see a lot of problems where they ask you stuff and they give you a graph, so you have to figure out that the problem is solved by knowing what the impulse is. Like for example, in a certain time period, what is the average force on the thing? Well, I don't know. Like if I went in here and I had T1 and T2, well, if I could definitely use this formula here, right? But I don't know. I know T, but I don't know J and F. So, but I could come over here and I can figure out what the J is by just calculating the area somehow. And then if I stick it in, and then I know what the delta T is, so then the average value of the force during that time period is going to be that impulse that I calculated from the graph divided by the time over which I calculated that impulse. So stuff like that, problems like that, you might get, Or maybe they ask you like the velocity, maybe this represents, the average value of a ball hitting the wall. So they ask you something like, what is the, I don't know, velocity, initial velocity. So, well, again, you do the same thing. You get the impulse from the graph, and then you come over and use this formula. So maybe like the final velocity through, when the of the collision, not the rebound, but like, so it might ask you, a ball takes 2 seconds to collide on the wall, and they give you a graph or something and showing you where that would be the maximum value. So I don't know. They say something like, what was the initial velocity, if the ball had final speed at its max, when it just was compressed. So you would extrapolate that it took half the time to compress to go to zero. Like at this time period, it would be at maximum value. So you calculate this area right here, that's going to give you the impulse of half the trip. And then if you think of the final velocity as zero, then that term goes out. You got the impulse, and you could calculate the velocity. You go like the J would equal to mv, where v is the, I guess that would be initial. Final would be here, so E would be equal to, and you're doing the magnitude, so the initial velocity or something. I think you see what I'm trying to say. You could just figure out what the impulse is, and then manipulate the formula in whatever based on implicit information that to figure out what the speed is just before it hits or something like that. So those are the kind of problems that they give you with impulse. I'll let you read that and try to maybe work some examples. If you have any questions about the problems, they usually don't give you a lot of problems about that. So I'm not going to do those in fact. You could probably figure those out. But these are all the different scenarios in the context in which you would experience impulse and see it practically given. Definitely understand that it's the third physical concept that we've seen now that has relevance to the area under a curve. So that's all I have about impulse. Any questions, problems, troubles, gripes about impulse? And impulse, so impulse by definition is equal to this thing here, integral of f of t dt, or average value of force times delta t. And impulse is also equal to the change in momentum of an object. So they have the same units, impulse. Momentum has the vector kilograms per meter per second, but impulse also has the same units. Another place where this kind of applies is, you give more practical application, is boxers. Anything where you have to hit, like, and there's apply a force over a small amount of time. Anybody box or do any kind of fighting, any kind of thing? What's the idea about jabbing? When you jab, how do you want to, like, your form has to be really, what I'm alluding to in terms of the time, like the application of the punch, right? What is significant about the application? If you have a certain amount of force and you can only apply that amount of force, would you want to apply that force over a long period of time or a short period of time, and why?
Short.
Sure, absolutely, Abdul. Why?
You will get tired, and you're not gonna have that much energy. I mean, you can't just do that same force for a long time.
Well, that's true. So, but I'm not talking about the time, the overall time in which you're fighting. I'm talking about the time in which you apply a punch, like a single punch. So
You
if you
want to,
have a,
I
say
think you
again,
want to, I think you want to deliver a heavy blow.
you want to
Like
do a what?
deliver a heavy blow, a heavy punch. If you do it,
Well,
if
well, heavy implies the force. I'm talking about whatever your amount of force you can apply, whatever that is. Sure, you want it to be as large as possible, but there's also another element to it. It's not just how strong you are or how heavy, because I'm assuming that heavy means the maximum amount, how much force. That's the magnitude of that. But what I'm suggesting is that for a given amount of force, you could apply it several different ways. You could apply it slowly or you could apply it more quickly. Which one is more efficient or which one is better and why? So heavy doesn't necessarily imply quick or slow. That's the point I'm making.
Quickly to get the work done. Mm.
Quickly, the work is going to get done either way. If you land the punch, but why is it more effective if it's done over a short amount of time as opposed to a long amount of time? This actually is my question is going to give the distinction between force and impulse. Up here, I showed them mathematically, but there also is an intuition about it that if you watch a lot of sports like boxing or what's the big thing now in WWM? What is it? No, that's Worldwide
UFC.
Wrestling. UF, yeah, UFC. You see it there a lot as well,
Yeah.
if you know what you're looking at.
is it so that the opponent will like take a lot of force and won't recover from the punches or something?
Say that one more time.
So that the opponent will take a lot of punches and won't recover, and you win.
What was the first part of that sentence? The what will take a lot of punches?
The opponent, like your opponent, the person you're
Oh,
punching.
well, yeah. Like that's going to be a certain amount of tolerance that person has, but the way you deliver the punch can make your punches more effective depending on depending on your technique and I mean, another good example of this is somebody like Bruce Lee, mixed martial arts, which I guess you do get in that. But like Bruce Lee wasn't a big guy. Like he was small. He was really, really tiny. Like he was probably like, I don't know, maybe 140 pounds or 50 pounds. Like how, if I look at how much of Bruce Lee, I mean, he was very toned and he was strong relative to his, but he wasn't that strong actually. You know, he was extremely like otherworldly quick.
He was
So,
impulsive.
well, yeah, I mean, his force, he could generate a lot of impulse. That's how I would say it, because he was so fast. So yeah, he was stronger than the average person because he worked out and he was toned. But relative to somebody like, probably people he were fighting, like these big guys, he wasn't as strong. He wasn't even even near as strong as him. Probably wasn't even close. Now, how could you be strong as some guy that can, some bodybuilders? I mean, you can't be being that small. There's no way. But he could punch harder than they could, harder, because he was so fast. So what does that have to do with what we're talking about here? It's very important. What does quickness have to do like with the thing, particularly if you're landing something on somebody's head? Because you don't have to be strong to knock somebody, like you don't have to be stronger than somebody to knock them out or to hurt them. What you have to be is efficient, quick, and know how to put the force right at the place where you want to put it. That's what he was. That's what the whole discipline of martial arts is about. And boxing too, for example, someone like Muhammad Ali, right? Sure, he was was heavyweight, but he was quick relative to much quicker than most heavyweights, much quicker than most middleweights, or even Like he was so quick. And again, coming back to that. That's how you could beat somebody like George Foreman, who clearly was like, if you look back at those fights, the Thriller in Manila. I mean, George Foreman. No, that was Frazier. Well, I forget the one where he fought George Foreman, but it was one of the African countries. I mean, come on, George Foreman was so strong. It was out of it. I mean, Muhammad Ali was not as strong as George Foreman. That's why everybody thought he was going to lose. But he was quicker and he was smarter. So this is the thing that I'm talking about. Why? What's the thing? I mean, you're kind of dancing around it, but you're not saying it very specifically.
He was
Last chance.
efficient, time efficient, or something.
It's time. It's time. It's the difference between impulse and force. And it's right here. It's here. Let me redo this. Let me change this around a little bit. If I take this equation here and well, yeah. I guess yeah, maybe this is the way to do it. So yeah, maybe I can do so. J over delta T is equal to F. That's a little bit better way to see it. Let's look at the magnitudes. So I kind of think about impulse as more like a force term. A force term. In fact, let's do this. Let's take these. So I've divided this by T, but I'm going to take this equation and plug it in here. All right. So here you go. Delta P, basically, and it brings you back to Newton's second law, basically. But remember what this is. This is mv final minus mv initial. And in the case of a boxer, that's a person's hand or arm. Well, clearly, when the thing comes to you, you throw the punch, when you're in the middle of landing the punch, the final velocity for half a punch is 0. So ultimately, what you're talking about is the initial velocity, which you start the punch, and the mass of the arm over some delta T. Now think about this. This mass is a constant. So there's only, in fact, this whole thing here could be a constant. Like you're only so strong, so you only have so much power. And that is going to translate to how fast you can start your arm, right? So you can only have a maximum velocity based on, how fast you can react and do that sort of thing, or how much force you can put in that. But if you have quick twitch muscles, or you learn how to do it very fast, or you have a really good technique where you do it fast, how does that affect? So what I'm trying to say is that this term here, the change in velocity, is related to impulse, which is more so related to, if you kind of look at the relationship between these two, it's like, yeah, impulse is associated with both, but there is only a certain amount of power that you have based on your muscles and how much you work out. But if you focus on quickness, if you can deliver that amount of power over a short amount of time, then this number goes up considerably. You throw a slower punch, and it's not really about slowness. It's really about how much you can draw your hand back once you deliver the punch, right? If you can throw all the power in the world and just land the punch and keep it there, the impulse, the amount of ability to translate that force to the thing you're punching, decreases considerably than if you can throw it, but then time it so that you pull it back while you're throwing it. That's what the whole thing about a jab is, about like whipping it, And the same thing with martial arts. When you see Bruce Lee throwing a punch, he doesn't throw it and keep it on the thing. It's more like, there's, that technique is a little bit different, right? Like you can really see a boxer when they snap the punch. That's the whole point about it. is about delivering the thing very quickly. Martial arts fighters is a little bit harder to see that because they don't necessarily draw their hand all the way back, but there is a quickness there, right? With everything, with the kicks, with the punches, everything. It's about trying to decrease the amount of time in which you're delivering the blow. So it's not just about strength. In fact, with someone like Bruce Lee, he shows just just he shows so significantly how how much technique is so important because you can only get so strong. And I guess you technically speaking, you can only get so fast as well. But a lot of people work more so on strength, building, bodybuilding and stuff, and it actually decreases their ability to be quick. But if Bruce Lee was someone who kind of worked on, I would say, quickness more so than strength, because once you reach a maximum amount of strength, for it starts to decrease. Like getting bulky and stuff starts to decrease the amount of time how quick you can be, and so there's a critical point there where it becomes less efficient. So it's not just about strength; it's about quickness and strength. And you want to try to get to a place where if you're a fighter, where you have the maximum amount of strength for the maximum amount of ability to deliver that strength through the power of a punch. So it's both quickness and strength, to focus on both of them. Because as you can see here, if this number gets smaller, there's a regime where just a millisecond, and certainly a second, increases this number dramatically, given that this number is a constant or is at its maximum value. And so then it becomes about technique. So does that make sense? And the thing is, it's also about like placement, because it's not just being able to deliver the punch. It's like moving, trying to not be hit, but also you want to punch in certain places. Because what happens is if you deliver a punch very, very, and the best place for like with boxers is right on the chin, not the head, not the face, right on the chin. Why? Because it makes the head snap. That's where the head pivots. It's the best place to make the head pivot. Again, impulse. Because what knocks somebody out is if you make their brain hit against their skull. That's what knocks somebody out. You make it pivot, it whips the brain, like it's almost like it causes the head to move so fast that your brain kind of knocks against your skull. And that's what knocks you out. So the faster you can do that, then the more like you can shock somebody and it causes them to faint out. That's why some people like who are really good at it, it almost looks like like when you see these fights where someone will knock somebody out with a jab and it looks like they didn't hit them that hard. Well, it's about where they place the punch. I think that happened in one of the Ali fights. It happens periodically. It happens where someone is like doing a punch and then the guy just falls down and it looks like he didn't get hit at all, or the girl or whatever. That's what's happening. They've placed the punch in a way that maximizes the impulse, both for the delivery of the punch and for the place where the punch was placed, because it causes a maximum impulse based on where it was hit. Or things like the heart punch, like like in those old Bruce Lee movies, you see that all the time, right? Like the heart punch in the chest, because you're delivering impulse to the heart. And you're doing it in such a way that it just, for that instant in time, it delivers that force, to that place, and it knocks the rib cage against the heart. Like it, you can increase that, or breaking blocks or bricks or things like that. That's what's going on. It's not just about strength. It's also about quickness and delivering impulse to a very critical point in the place where you're trying to to the place where you're where you are trying to create the maximum amount of damage, essentially. Yeah. So yeah, this definitely has a practical application. Maybe that'll help you remember it a little bit better. Same thing with like batting or golfing. It's all the same. There's a sweet spot on the bat, right? The technique, that's why golfing technique is so important. It's not just about like you, it's about like the point at which that contact is making contact with the ball. It won't want to be the most efficient thing. So the quicker you can do that for the place in the swing, the better. And there's different places. Like that's actually a good example. How does everything that I was saying with boxing apply to golf? Well, as it turns out, you know, they have that whole shape that they show, right? You know, in the swinging motion. Well, there's a place where if you could be consistent, like, you know, for like if you had a machine, right? The place where in that swing where the ball is in contact, there's two things you're looking at. It's force and time. So clearly when you're like the thing is right here, the club is not going as fast as it can. There's going to be a place where it's going to reach its maximum speed, usually somewhere down, you know, in an angle of where, you know, where it's falling just before it starts to rise again. So that's where you're going to have a maximum force. But also there's a critical point in that the angle where the ball also will be in contact longer or shorter depending on where you're swinging. And so if you can have great technique so that you're always hitting the ball so that you're a maximum amount of force, but it's at a place in the swing where it's the minimum amount of time in contact, then you have the largest impulse. And so again, that's why technique is so important in golf, because you want to get to a place where you're consistently doing that all the time. And so with a maximum impulse, obviously you're going to have, you know, a larger. So it's not just about how strong you are, and it's also about how, you know, how well you can place the club on the ball so that they're in contact. You're applying the maximum force over a shorter amount of time, and that's what's going to give you a larger, I guess, play down range. So yeah, impulse is important in all these kinds of things, these kinds of collision sports. Yeah. So any questions about any of that? Okay. Yeah. And I will wrap it up with one last thing. I told you I was going to do conservation of energy, and then because collisions, that's the larger. We got a lot to talk about there. Wouldn't have had time to finish it, but I can introduce in the last 5 minutes the third conservation theorem, or the second conservation theorem. We've seen conservation of energy, and the criteria there is that you can only use conservation of energy whenever conservative forces do work on the system. Conservation of momentum is just as important. In some ways, it's more important than conservation of energy, because you can use it in more cases than you can use conservation of energy. You can basically use conservation of momentum almost all the time in terms of the practical problems that we're using. Conservation of linear momentum. Here's the deal. Come over here. Conservation of linear momentum. First, start with Newton's second law, the version that I taught you, second version. The net force on a system is equal to the time rate of change of linear momentum. Okay, the criteria for that momentum is conserved. Remember, Newton's second law said this is the net external force on the system. So the criteria that linear momentum is conserved is that linear momentum is conserved if the net external force on the system is 0. Actually, looks like the first law, isn't it? So basically, you can say that if the first law is satisfied during a collision or an interaction of a system with, of two particles within a system, then linear momentum is conserved. How? Well, plug equation 2 and do equation 1. When you do that, you get that 0 equals dp dt. And maybe some of you more mathematically oriented folks know that there's only one criteria physically in which equation 3 can be satisfied. What is the criteria under which dp dt equals 0? Anybody? Let me write it a different way. Let me make it a delta quantity. What is the criteria such that delta P over delta T for a system is equal to 0? If you're observing the system over a certain amount of time. Kind of a trick question. If you're observing first of all, a couple reasons. If you're observing the system over a certain amount of time, will delta T ever be 0? Muhammad, will delta be 0 if you're observing over a certain amount of time? Oh, he said no. Tommy
No.
said no. So good. No. So, and the other reason is that even if it were 0, this means that this is undefined, which is not the case. It's not realistic. So basically, in order for that to be satisfied, delta T can never be 0. So the only way that that could be satisfied is if delta P is equal to 0. And if delta P is equal to 0, that means that P final minus P initial equals 0, which means that P final equals P initial, which is conservation. Well, in all three of these, actually, it's conservation of linear, means that the momentum of the system was conserved. It's the same before and after a collision or two different time periods, whatever. So the criteria that linear momentum is conserved is that the net external force on the system must be 0. Doesn't have a conservative, non-conservative force, doesn't matter. All the forces must add up to 0. If that's the case, between a certain time period and a certain delta T or during a collision, then in that time period or during that collision, linear momentum will be conserved. And you can use that as a means for solving problems. Okay, I'll let you go. That's it for today. So that's a biggie. Go ahead and continue reading through that chapter, momentum. Read through the collision stuff, because that's a whole different, it's applications of this conservation of momentum and conservation of energy. And we'll look at that. There's a lot of algebra in that involved. And we'll knock that out during half the class period on what's the day? Wednesday, on Monday. And so we will be into rotation. We'll get into rotation by Monday as well. So
Professor,
it's going to go ahead.
do you say you're going to give us a take-home exam?
Yeah, I'll open it. I'll post it on modules by the end of today.
Okay.
And so you have a couple days to turn it. But remember, it's not like the quizzes. I'm going to put a time period on it. So you're going to have to block out. I would block out at least 2.5, 3 hours to take the test sometime between now and the time you have to turn it in, which would probably be like Monday or something. Yeah.
The assignment, it do take us like 4 to 5 hours to complete it. So I hope the test won't be like the assignments.
Well, I just told you I'm going to give you about 3.5 hours to do the test. So that's what. So what are you saying? Is it too long? You think too? I mean, you mean the homework assignments? Because certainly the quizzes don't take you 4 hours.
No, the quizzes are okay, but like the test, the homework takes like 4 to 5 hours to complete it.
Yeah, that's about right. I would say that for about 4 to 5 hours to learn a chapter in physics. I mean, given how much stuff, I don't think that's. I mean, how long do you think it should take?
No, okay, so no, I said this just because of the test. The test, you should give us like almost the same time too, because if it is going to be the same level of difficulty, then it should be the same amount of time.
That's not necessary. No one gives you 4 hours. If you were in a regular class, you don't get 4 hours. I mean, you get 4 hours maybe to take an exam. I do give unlimited time on the final exam, but no, not for a test. There's got to be a little pressure there. So you actually raise a good point. I'm not being facetious. you do raise a good point, which means that given your logic, that means you haven't made any progress. Because when you're doing homework, you don't know the material. You're trying to learn it, right?
Yeah.
So yeah, it's going to take you longer to kind of work out all the details and work out all the kinks. But presumably, once you know it, it doesn't take you as long to perform. Which means that learning and preparing for a test aren't the same thing.
Yeah.
For me, I make a distinction. I am learning the material. Now, have I learned it? Do I know it? If so, when I go back and do those homeworks, it shouldn't take me 4 hours. If it does, then I don't know it. So that's the criteria that I use. I mean, think about it. What if I were up here and it took me 4 hours to explain this stuff to you? Like you would go take another professor. Now, I'm not saying you have to know it as well as I know it, because I've been doing it longer than you. But there is definitely a difference between your ability to perform while you're learning something than it is after you've learned something. And that's why I make the tests are not going to be as long as the time period. It's kind of giving a little bit of pressure there, which means you got to know it better than you did when you were learning it. As you make a very good point. So even though this is a take-home test, it's still a test. So, you got to be a little bit more prepared. So that there's a little bit of pressure there. Not much, not a whole lot more, because it's still take-home and you got days. There's definitely less pressure than taking it in class. But keep in mind, we still got to try to, that pressure is good over the long period of studying and learning. It's, that I'm not taking that all away. It's still there a little bit. So try to be as prepared as you can, even though it's a take-home test, so that you can, keep that in mind. You want to know it a little bit better than you did when you were doing the homework.
Okay, so like how many questions are we expecting?
I have to look and see. I'm going to try to make it something reasonable, but usually, I'm choosing like the quiz is about 5 questions. Usually the tests are just like class, like anywhere from 15 questions, to 20 questions maybe. It's about the same as the homework, right? I would say. I mean, I usually give maybe more for the homework though, but like I could even give up to 25, 30 questions on the homework. But the test, anywhere from, it just depends. It depends on the questions, but I usually go from getting less than 15 questions on a test is a little bit short. More than 25 questions or 30 questions is a little bit much. So somewhere in there, 15 to 20, so there's definitely some pressure there, depending on how difficult the questions are. That's definitely what I would give you in class for a 2-hour test or 3 hour, certainly 3 hours. 3 hours is getting a bit up there. So there's some pressure. You got to work.
That's a
You got
lot
to
of
work
pressure.
somewhat quickly. Say again.
That's a lot of pressure.
This is calculus-based physics, folks. Now I know that you kind of had a break because of COVID. I've been trying to take it easy, and I'm not gonna, I look at the grading. It's kind of hard to gauge, but that's what tests are about. There's a time element there. So that little pressure, you have to, if you study with that in mind, it makes your studying a little bit more aggressive. And over a long period of time, you learn more. That's why people test. So, yeah. Yeah. We'll get through the first one. I know it's been a while. We should have had it long ago, but these are different times. But I'll take it. I grade very, very fairly. So if you get the test and you come back and all the grades are much the average really low, then I'll take a look at what happened and have to kind of work it out. There's no absolutes, and I think I'm pretty good about taking that into consideration. And certainly this is new territory for everybody. But if you're trying to have no pressure, then as an educator, I have to push back a little bit. There's a reason that people do that. And so try to embrace it. And I'll try to be as fair as I can. All right.
Yeah, sound good.
Okay. All right. All right. I need to go for a walk. Been in here all day long, cooped up. So yeah. Be safe, folks. Things are ramping up with these the COVID. So COVID the cases. So
Thank
be
you,
careful.
Professor.
All right. Thank y'all. Be well.
Professor,
Yes.
I have a question.
Yes.
So this relate it has to do with work, right? It's not on the top of the cover today. Um, if two balls, right, are thrown, two balls of the same mass are thrown at a wall at the same velocity, one reaches the wall and the other doesn't. Is the work done um, on the balls the same or no?
The work of what?
The I say drag the work in reducing the velocities of the balls to zero, because obviously one reaches the wall. That means it's the wall that stopped it, but then the other that didn't reach the wall, it was more of gravity that uh, stopped it.
Gravity. Gravity is in the opposite direction. If it's a horizontal.
Drag, my God.
Okay, so you're saying that the balls were thrown with the same initial velocity,
Yes,
and they are thrown with the
they have the same mass.
same mass. Were they the same distance away from the wall, or
Yes,
no?
yes.
They were.
Mhm.
So then they're going through different fluids, because that's the only way the drag force would be different.
Okay.
I mean, that's a question. Is that
But that's not how the question. That's not the question. We just asked to compare the work done uh, in bringing the velocities of the balls to zero. So we're supposed to compare the work done by the first ball and then the second ball. Which
so? The second ball was in a vacuum and it just hit a wall,
yes,
and the first ball was in a place where there was no vacuum, but the horizontal velocity went to zero.
yes.
Okay. Um, that's a good question. Let me ask you a question. What concepts are applicable?
Applicable.
Yeah, applicable.
In the second scenario where the ball was thrown in the first scenario where the ball was thrown in a vacuum, there's no other force acting against the ball. Like there's nothing like drag acting against. It's only gravity that could act on the ball, but I don't think it would stop the ball from reaching the wall, right? So, but in the second scenario, drag is present.
My question to you is, what concepts have you studied that are applicable in both cases?
In both cases,
Yeah.
the first one I'll say Newton's first law. Then the second one I'll say Newton's second law.
Okay. Well, you're asking about work and Newton's laws. There are other concepts that are work related that they might involve forces, but they're not directly like Newton's laws doesn't directly associate with force. Newton's first law associates with nothing basically, and Newton's second law associates with acceleration. There are some concepts that we studied that directly associate force with work. What are those concepts?
Drag.
Well, drag doesn't, no, drag doesn't necessarily, it's not directly associated with work.
There's isn't there also the work? There's work done by drag.
Yeah, it is, but it doesn't have to be. I mean, well, I guess it would have to be, but you know, there are concepts that actually define, like what concept defines what work is.
Uh, Voice and distance.
Yeah, that's what do we call that concept? It has a name, or I gave it a name.
Oh, mechanical energy.
Well, mechanical energy is mechanical energy. That's not work, but it's the definition of work. Work is the integral of F dot dx or F delta x if it's a constant force. That's the concept that directly associates force with work. What's another concept associated with work that we talked about?
The work energy theorem.
Work energy theory. Good. Now you're on the board. Where it equates work with the change in kinetic energy.
Yeah.
What's another concept that we associate with work directly?
Hooke's law.
No, that's force. Force equals kx. That's just the.
Oh, okay. Yeah, that's
Now
true.
the hooks of a spring can do work, but it doesn't directly associate work with concept. The other one is the general definition of potential energy. Work equals a negative of the change in potential energy. Now, it sounds like the question asks you something about how much work does it require to bring the object to rest, something like that.
Sorry, I didn't get that.
You said that the question asks you to associate work with the object coming to rest, right?
Yes, yes.
So which of those concepts that we just went through is the concept that would most directly be applicable in this problem?
The potential energy.
Is potential energy associated with speed or velocity directly?
No. Okay.
Okay, so no.
Kinetic energy is directly associated with speed.
Okay, so of all the concepts that you mentioned, I would start with thinking about the concept of the work energy theorem because it directly associates a change in kinetic energy with work, which is directly associated with a change in velocity. Yes?
Yes.
Now, you were probably thinking about the concept of force, which are related, but they're not directly related. So it's harder to understand. Now, we know the force is what's actually causing the work, but indirectly, the work indirectly affects the change in velocity. I mean, the force indirectly. It's more like force causes work, and then work causes a change in energy.
Mm-hmm.
All right, so I would probably think about the work energy theorem. Now let's go back. In the end, they had this, how much kinetic energy did they have? What was the comparative kinetic energy as soon, for both objects as soon as they left the person's hand?
The kinetic energy will be the same.
Yes, because the velocity was the same. That's right. Now the question asks you about in the end, the final, when they're at rest, right?
Yes.
Like, okay, so when the objects are at rest, what's the final kinetic energy of each one?
0.
Okay, so it doesn't matter what happens in between. It doesn't matter what the force is doing or what type of force it is. The work energy theorem only deals with the final kinetic energy and the initial kinetic energy.
Mm-hmm.
So in both cases, if they had the same initial kinetic energy, and in the end they had the same, yeah, how does the change? How does the amount of work compare for each force?
It's the same.
It's the same. Yeah. So I would say it's the same. Now, it doesn't mean that it happened in the same amount of time, but the problem doesn't ask you that. That what's happening with the force, it could be larger. Who knows? I don't know. We don't even know. But that's the power of something like the work energy theorem. And I'm assuming you probably would have to assume that it's a conservative, like nothing's energy is being taken out, or there might even be several forces. We don't know, but because it didn't, but basically the change in kinetic energy in both of those problems would have to be the same. So whatever combinations of force or forces act that did that comparatively, it would be the same amount of work done.
Yeah.
Yeah.
Okay, that makes sense.
Yeah. So again, I would look at your technique, your problem solving technique, because I don't think you didn't understand, you couldn't have gotten that question, but your technique didn't allow you to look at all the possible concepts associated with. That's why I start a problem like that. If you just were thinking about force, you would never get it, even though you might have the ability to get it, because you know what I mean? So again, technique is very important. Start, that section, once you have all the information and you understand the setup, which basically steps 1 through 5 takes you to 1 through 4 takes you there. Step 5, that's where I started by when I queried you. What are all the possible concepts that apply to this problem? All of them. So yeah, Newton's laws are definitely a part of that. But if you look at other concepts, they may not be the concepts that are directly associated with the perspective that they're asking you about. So it's harder to see the answer, particularly in a qualitative question like this.
Mm. Yeah, that I think that was the mistake I made, because once I saw that they both had the same mass and they had the same acceleration, no, they had the same velocity, my bad. I just assumed that, oh, okay, the same force was probably applied on the balls initially, but then they didn't cover the same distance in the same amount of time. So I was just like, okay, so obviously the the work done between both of them will be different, but apparently I think that was not the case.
Yeah, it's not the same. Because it's not the same force, so they're not acting differently. And again, that is the advantage of the work energy theorem stuff. All of those things, work energy, definition of concept of potential energy, and the ultimate, they ultimately combine to give conservation of energy. That's the advantage of being able to use it. Now, the thing is, conservation of energy only applies when you're using conservative force, so you probably wouldn't want to go there. But you could just stop with either work energy, or basically work energy is the thing, because with work energy, it doesn't necessarily have to be conservative forces. That statement is true even if it's non-conservative forces, that the work done is equal to the change in kinetic energy. And it doesn't matter what's happening in between the 2 points, the beginning and the end. The only thing that matters in that concept is, can you figure out how much kinetic energy changed? If so, then whatever forces caused that to happen, no matter how it happened, all those forces, that was the work that those forces did.
Mm-hmm.
Yeah. So that's the power of that concept.
Okay.
And of course, you don't have to evaluate any forces or anything like you would have to do if you were trying to apply Newton's laws. Because in order to do the definition of work, you got to know what the forces are doing, right?
Yeah.
And in that problem, there's no way to know that. So
because you actually didn't state any forces.
Yeah. So you really can't use the definition of work, because that would mean that you would have to use Newton's laws, and you don't have enough information to do that. So it really shows the subtle differences of those concepts and the value that they have, in working problems. It's a good question. Does that help?
Yeah, that helps a lot.
Yeah.
Thank you very much, Professor.
Yep.
Cool.
All right. Have a good one.